All right, we're going to learn about how to set up integrals. First example, we got a length of rope L. I want to calculate the length. I'm going to divide this up in infinitesimally small little pieces of dl, differential, if you will. And I'm going to add those little pieces up from 0 to L. And that is going to give us L from 0 to L. We get length L. Okay. All right. So now we're going to take our circle of radius r and calculate the area. So that's going to be a little differential infinitesimal slice of pizza. Okay. To find the area of that, we got a little, let's see. So I'm gonna add that up from 0 to 2 pi. Not 2 pi. Yes, 2 pi. Not 2 theta. 2 pi. Does that make sense? Problem is, this needs to agree unit-wise with the limits of integration. Have to be the same. This isn't a wrong statement. I just can't evaluate it in that form. Does that make sense? Okay. So I need to figure out what's an expression for dA. How can I figure out the area of that sector? I think there's an equation for a sector, right? Area of a sector. I think there is. Pretty confident. I don't remember what it is, but it's there. The equation for area of a sector.
Theta 360 times pi r2. According to third space learning, the area of a sector is a part of the area of the full circle. It can be found by using the formula. Theta 360 times pi r2.
Yeah, that's not it.
The area of a sector is 8 times pi r squared.
It's close to this. Maybe 1/2. What? Pi r squared theta. No. I think this is right. Yeah. Jim.
Can we just say it's a line and then just say it's just 2r?
Great question. I need. Ooh, I do need r squared. Does that look good? Okay. Here's a really important thing. This, watch this, guys. This is like crazy important. This has an area, a unit of meters squared. This also has to have a unit of meters squared. Has to. Okay. Theta is unitless, radians. So length over length. Okay. So this has to be That's how it tipped me off. Like, oh, I probably should square that. Okay. And we'll find out if we're right real soon. Just that.
If DA, or debate, whatever you want to call that, if that is units of that is meters squared, wouldn't it become meters cubed when you take the integral, which would be units?
Great question. No, because I'm not multiplying anything. I'm just adding up a little piece of this, little piece of that, little piece of that, little piece of that. I'm just adding up. Okay. And multiplication, if you think about it, multiplication is just taking, like, if you're like 5 times 7, it's like taking 5, 10, 15, 20, 25, 30, 35. You're just adding those 5, 7 times. I'm adding dA infinitesimal times from 0 to 2 pi. Okay? Everybody all right with that? Okay. Now, R is constant. You all right with that? Capital R, it's just the radius of this. That does not change. So I can pull that out. Anything that's constant, I can pull out. So now, this agrees unit-wise with this. That's a good place to be. Okay, we have to be there. So this ends up being theta from 0 to pi. So that ends up being and what do we know? We end up with that.
Could you also like use like
Hang on. Yeah. Yes. I'm not okay. I'm going to steer away from this, but this is probably the most intuitive way to cut the circle. Does that make sense? Mathematically is not the easiest. We're going to do an easier way here momentarily. That's why I don't have a sector area memorized. So I never use this other than this slide here. Okay? But does this make sense? What we are doing and why we're doing it. Okay? Here's the takeaway. The unit of this has to match the unit of this. This is a correct statement, but I cannot evaluate it as it stands. So I need to make some kind of relationship between the unit, or like the measurement here, and the measurements. Okay, so either I need to change these or I need to change this. I chose to change this in relation to theta. Okay, the other thing I want you to walk away from is the unit of this has to be the unit of this. Has to be. This will save your bacon if you like. That's a good when you're creating this stuff. Okay. All right. So a more mathematical friendly way to cut this pizza up is to make concentric rings. Okay, is that where you're going, Tyler? Okay. So here's the deal. The area of this ring is dA. I'm going to add this up See if you can figure out what the limits of integration, where am I starting and where am I ending? Okay, where am I starting? 0. What am I integrating? Like, what's it? What am I going until? Capital R. I'm starting here, little bitty, itty bitty, getting a little bigger, okay, until I get to here. Okay. Now, does that make sense? Okay. So I'm looking at the area of the ring. So, does this jive with our limits of integration? What's the unit of dA? Meters squared. What's the unit? Meters. Does not work. Okay. So I need to come up with an expression for what dA is. Okay. Here, check this out. Ready? If I come over here and I snip this, and then I unroll it, what's the length of that? If I take this, snip it, and then and lay it out here, what's the length of that, Jared? It's the circumference of that ring, 2 pi little r. A lot of times in this class, what I'll do is I'll use a lowercase variable to distinguish the thing that's changing. And the capital of that variable is like the fixed, like we're going to the final radius r. And we've got a little changing radius, little r. Does that make sense? Okay. Now, what's the unit of this? What do we have so far? Meters. Uh-oh. How do I find the area of that? I've got the length. What's the width? The width is a little change in dr. Little change in r. Does that make sense? Like I stepped it out just a little bit. And the thickness of that ring is dr. That has a unit. That unit is meters. They will not teach you that in math class. They use this just to say, what are you evaluating the integral? It means something in physics. Okay, it means something in story problems. It's a little infinitesimal change in radius. That's the thickness of that. Okay, so this checks. You good with that? That makes sense? So I'm adding up the area of each of these rings all the way up. I'm going to pull out anything that's constant. Okay. I guess, sorry, before we dive into this and this must agree before we can take the integral. and this, the units of this and the units of this must agree. Okay, that's your double check. That's your quality control. Did I hit this right? Okay, so we got 2 pi 1/2 little r squared from 0 to r. We got 2 pi times 1/2 r squared minus 0. Craziness. No way. Didn't see that coming. 2 pi r is the area. Good with that? James?
Since you have R and then DR, isn't it still meters squared on the inside?
Right here, it's meter. You got meters and you got meters. Once we've evaluated that, we take that dr goes away, and so the meters squared is wrapped up with this. Is that what you're asking?
Like you said that we couldn't take the integral if we're because the big R is in meters and the inside was in meters squared, so we couldn't take the integral.
Oh, good question. Okay. Let me. Okay, so the question was, I thought this was meters squared and this is meters. How are we able to take the integral of that? So this by itself must have the same unit as this by itself. This variable must agree with that variable. It's not this whole unit. It's just this unit by itself has to agree with that unit. Okay. So there's a lot of points of like quality control that we're trying to set up. Okay. Things get really complicated really fast, but if you keep these checkpoints, if you're faithful to those, it'll go well for you. Okay. Try to set it up conceptually first, and then try to figure out how do I get this chunk, this infinitesimally small whatever, to agree with the limits of integration. Make sure that these units agree once you've evaluated, like once you have concocted your little piece, and then this and this have to be the same variable once you evaluate it. This and these have to have the same unit. So there's a lot of checkpoints. Okay. And then you can do math. Okay. This is the skill that I'm trying to develop in you. This, that's just math. Okay. Ready? All right. So back to our rope. If we have uniform length L, mass M, uniformly dense, okay? If I had a little like monologue on uniform density, uniformly dense, okay. Density, this is just general knowledge, mass over volume. This is volumetric density. Go for it, Hannah. Go for it. Okay. Let's say we didn't care about the volume, but we just had it spread over an area. This is mass over area. This is surface area density. If it was a two-dimensional object. Okay. If it is a one-dimensional object, this is known as linear density. What thing in real life can be considered linear or a one dimension? Well, a rope. The length is way bigger than the height or the depth. It's negligible. It doesn't play that much, doesn't carry that much influence. Okay? So, if they say uniformly dense, you're gonna, like, that should tip you off, like, ooh, I need to set up one of these, depending on if it's like a one-dimensional object, like just the length, like a rope. Is it an area, is it like a sheet? Or is it like a volume, like a cube? Okay. So, that's a little background, just densities. So, coming over here, I'm going to calculate the total mass. I already know what the answer is going to be. It's going to be capital M. Chunk this up in little chunks of mass. Oop, nope. Let's see. What do I want to do with that? Yep, let's do that. Little chunks of mass. Okay. And I'm going to add up all those chunks of mass up from 0 to L. Can I evaluate it like this? Thumbs up, thumbs down. In this form, can I evaluate it like this? This unit does not agree with that unit. We got kilograms, we got meters. Definitely not. Okay. This is where our uniformly dense relationship comes in. I know that this is mass over the length. Okay. Since that's uniformly dense, I can say a little chunk of mass over a little chunk of length has that same ratio. This trick right there, you're going to use the rest of the year. 2025 included in that year, like the rest of the academic year. This trick right there. Okay. Well, instead of mass, we're going to use it for charge next semester. It's the same trick. Okay. So what I can do here is I can rearrange this. So we've got an entire mass over the entire length times dl is equal to dm. I'm going for something that is in meters here to agree with this. Okay. This unit-wise, I've got kilograms on this side. I've got meters, kilograms over meters. Meters cancel out. You get kilograms. Okay, we're good. Good with that unit check. Okay. So I can come up here and I can substitute in that. Oops. Okay. I can pull out anything that's constant. So M is constant. Capital M is constant. Lower capital L is constant. Unit-wise, this agrees with that. Can substitute that in there. M over L times L minus 0. Good question. So this L is not changing. This L is this length here. That is a fixed value. Does that make sense? So that's why I can pull that out, even though I'm like, find the integral with respects to L, F lowercase l, let's change this. This lowercase l is this some change in length, and that's like, all right with that? Okay. So, questions there? All right. Let's do the same thing. Let's find the mass. I mean, we expected to find capital M for this string. Okay. We've got we have a circle with a radius capital R, uniformly dense. It's just a circle. It's not a sphere. I want to figure out what the total mass of this circle is. It's going to be capital M, but I want to know what the integral is going to be. Okay. So I would like you to use concentric circles. I'll give you a minute head start. I'll start you on, I'll give you more than that. No, just, yeah. So I'm going to employ this surface area density trick because it's uniformly dense. I know the mass over the area. Well, I know the area is going to be pi capital R squared. That's the entire mass over the entire area. And that's going to be equal to a little chunk of mass over a little chunk of area. Just I. Yep. Okay. So keep going. That's kind of a checkpoint. Okay. What I'm going for is I need something in terms of meters. And I'm going from 0 to capital R. Those are in meters. This is in kilograms. Here, I've got meters squared. Closer, I mean, that's better than kilograms, I think. But I needed an expression for that, the area of that ring. The area of that ring is going to be equal to the length times the thickness. So here I've got meters squared. Here we've got meters. Here we've got meters. Meters squared equals meters. So now I can plug this into m over 2 pi r dr, which allows me to find m over 2 pi capital R times 2 pi lowercase r dr equals dm. How are we doing with that? Okay. Does this r cancel out with this r? Lowercase, does that cancel out with the uppercase? Okay. That's sort of different. I mean, they're not the same thing. This is lowercase is changing, so I can take this expression and substitute it in for dm. pull everything that's constant out. And now this variable agrees with that variable, which is the same thing. This unit and these units are the same. We can now evaluate it. So I get 1/2 r squared, a half and the 2 go away. Got m over r squared times r squared minus 0, and I get m as the mass of that circle. A lot of work for something we already knew the answer for, but the point is, how do you set this up? Okay, how are we doing? Like, I want to take this slow and steady because this skill is essential. And it has a tendency to be sticky. Okay, good with that? Aiden.
What does the straight up and down one mean?
Oh, it just means after you've done taking the integral, what limits this is. It means, hey, I've already done that limit. Sorry, that integral. I've evaluated the integral, I think is the proper way to say that. I just need to stick in final minus initial. Does that jive with people who know what they're talking about? Okay. I definitely don't want to give you bad, inconsistent, I guess, explanations. Okay. Good with that? Okay. So what happens if it's not uniformly dense? Oh, buddy. Oh, we're here till 14 after. Okay. So, calculate the mass. So what I'm going to do, I'm going to chunk this up in little chunks of mass. And I'm going to add it up from 0 to L. Okay. Now, the density is no longer uniform. But what I can say is this is linear density as a function of length. So if I start here at L, make that the origin, and this capital L, and some length L to somewhere, we're going to have the same we're going to have a certain ratio. That's changing as it goes along, but this little chunk, whatever this little chunk is, has a certain density of whatever length, and that's mass over that little mass over that little length. You all right with that? So I'm going to substitute then 2L plus 1 equals dm dl. Substitute that from the problem. And then what I can say is 2L plus 1 times dl is equal to dm. I can stick that in there, 2L plus 1 dl. So I get L squared plus L. Okay. And it works out to I don't know what that sound is. That's a new one. Okay. So it works out unit wise because we got a funky unit here. Say we express that, it would end up like we would plug stuff in, it end up being kilograms. But
Wait,
yeah.
so, but our answer is meters squared plus meters.
So if you actually, you know, I think I should change that. I think there should be a unit on this one and then a separate unit. I think this should be kilograms over meters squared, and that's kilograms over meters. So when I plug that in, it's going to end up with kilograms. I didn't paint that very well. This is kind of a more mathy thing. You'll see this on the AP test, this type of thing, and they'll just leave it like that. Okay, good with that? Yay. We'll pick that up tomorrow.